Hey folks, welcome back. In this video we're going to go over diffraction gratings and the grating equation. So let's get going. Now we've already seen how light waves can undergo interference, and we're going to compare Young's double slit experiment here to this new thing called a diffraction grating. So it starts by saying, unlike Young's double slit experiment, which has only two slits, a grating consists of many equally spaced slits placed very close together. It then says light is diffracted through each slit, and due to the path difference to the screen, an interference pattern similar to that for the double slit is produced. Using a grating, i.e. more than two slits, rather than a double slit, lets much more light through, and therefore brighter fringes are produced and the fringes appear sharper. So passing light through more than two slits will produce brighter and sharper fringes. Gratings are normally used alongside a monochromatic light source, for example a laser, as shown below, or a white light source. So remember, a monochromatic light source is just light of a single frequency or wavelength, i.e. colour, or we're saying we could use a white light source here instead, which is going to consist of all the colours of the rainbow. Now this setup here shows you what it looks like. So here we could have a monochromatic light source such as our laser, where this light is passing through a grating, and in this example we've got a grating with 300 lines per millimetre. So what this means is that for each millimetre on the grating there are 300 lines or slits, and that means the light from the laser is going to be diffracting through all of these many slits here. You can then see we've got some fringes appearing on the screen where the angle to the maximum theta is labelled, and if this is a zero order maximum in the middle of the screen, then you'll notice we have the first order maximum here and then the second order maximum here. So just like we saw for Young's double slit experiment with only two slits in the grating, we get an interference pattern or diffraction pattern produced where we get bright and dark fringes. But remember, these are going to be brighter and sharper than those that we saw for Young's double slit experiment. Moving on, it says here it can be shown that the wavelength of the laser light and the fringe spacing are related by the grating equation. So looking back at the picture, what we mean by the fringe spacing is just how spaced out the fringes on the screen are. So that would be the distance between any two adjacent fringes. And that fringe spacing can increase or decrease depending on the slit separation, i.e. the distance between the slits of the grating or the wavelength of the light that's used. So here's our grating equation, which is d sine theta equals m lambda, where d is the distance between the slits of the grating, i.e. the slit separation, measured in meters. Theta is the angle of deviation measured between the central maximum and order of fringe being considered, measured in degrees. M is the order number of the fringe with no units. And lastly, lambda is the wavelength of the light measured in meters. Moving on, we have a top tip which says questions will often give you the number of slits or lines per millimeter on the grating, and you have to calculate the slit separation d before using it in the grating equation. To do this, you must multiply the number of lines per millimeter by 1000 to get the number of lines per meter, i.e. if we were to write this as an expression, we could say the number of lines per meter is equal to the number of lines per millimeter times 1000. But sometimes the question will give you just the number of lines per meter instead of the number of lines per millimeter, and therefore you don't have to multiply by 1000. You would only need to do this following part here to find d. So once we have the number of lines per meter, we can then use the following equation. d equals 1 over the number of lines per meter. So in order to get the slit separation or distance between the slits on the grating d, then we just do 1 over the number of lines per meter. And of course, some questions might be kind to you and just give you d straight away, so you wouldn't have to do any of this converting into the number of lines per meter and then using it in this equation. So going back to this equation, what we're saying is that the value of little d can be given to you in three ways. You will either be given the value of d straight away, and therefore all you would need to do is plug it into this equation, or you might be given the number of lines per meter, in which case to find little d you need to do 1 divided by the number of lines per meter, or the last case would be the most work, where if you're given the number of lines per millimeter in the question, then you need to change firstly from number of lines per millimeter to the number of lines per meter, remember by multiplying by 1000, and then to get the slit separation d you do the 1 divided by the number of lines per meter. So watch out for questions on diffraction grating where they're giving you d in different ways. Moving on, we have a question to think about. So it says, how does the fringe spacing depend on the slit separation and the wavelength? Well, we've got an equation d sine theta equals m lambda where we've got slit separation and we've got wavelength. But it's maybe not obvious that we have fringe spacing involved in the equation. But we'll look back at the picture here to help you understand how we do actually have something in the equation which tells us about fringe spacing. So remember we said angle theta here is called the angle to the maximum that you're talking about, the order number m, and it's always measured from the centre, the zero order maximum, to the maximum of interest. Now what we need to think about here is how the fringe spacing and this angle to the maximum are related. Well, if your angle to the maximum was decreased, then that would cause your fringes to appear closer together, so that would decrease the fringe spacing. So we can say that these values are actually directly proportional. So if the angle to the maximum theta decreases, then we could say that sine theta decreases as well, because theta and sine theta are directly proportional, but that also means the fringe spacing decreases, since sine theta and fringe spacing are directly proportional. So if one decreases, the other decreases. We could say the opposite is true as well. So if we were to increase the angle to the maximum theta, then that means sine theta increases, and therefore the fringe spacing also increases, and that would cause the fringes to get further apart. And we can show this by manipulating the grating equation. So it says rearranging the grating equation for sine theta gives sine theta is equal to m lambda over d. So all we're doing is dividing both sides of the grating equation by d. So we get sine theta equals m lambda over d. And we can then think about how sine theta is related to lambda and how sine theta is related to little d. So if we ignore the m and the d for now, we can see that sine theta is directly proportional to the wavelength lambda, and that's because lambda is on the numerator of the fraction here. So if wavelength increases, sine theta increases, or if wavelength decreases, sine theta decreases. And if we ignore the m lambda for now, we could say that sine theta is directly proportional to 1 over d, i.e. sine theta is inversely proportional to the slit separation, and that's because we have little d on the denominator of our fraction here. So what this means is if slit separation increases, then sine theta decreases, or if slit separation decreases, then sine theta increases. Goes on to say this means that the angle of deviation and therefore fringe spacing is directly proportional to the wavelength of the light and inversely proportional to the slit separation. Therefore, in order to increase the fringe spacing, we want to see what's going to increase sine theta. So here sine theta will increase if wavelength increases, so we could say increase the wavelength to increase the fringe spacing, i.e. we could move from the blue light end of the visible spectrum towards the red light end. Or in order to increase sine theta here and therefore the fringe spacing, we would need to decrease the slit separation. So it says here decrease the slit separation, i.e. use a grating with more lines per millimeter. And you might be thinking, well, how does more lines per millimeter decrease the slit separation? Well, it comes back to this equation that we looked at earlier. And so the more lines per millimeter, then that means the greater number of lines per meter we'll have, and therefore if that number on the denominator of the fraction is greater, then d will be smaller. So make sure you can remember these two relationships or know how to see them from the grating equation, because by knowing those two relationships, you'll be able to work out how to increase the fringe spacing. So to summarize, remember we can say to increase the wavelength or to decrease the slit separation. Lastly, I'll just show you a quick simulation to help you visualize this. So here we have an example of a simple grating used, which is just two slits, so this is essentially Young's double slit experiment, and notice how we have our straight line planar waves diffracting through the two slits here to create our circular wave patterns which overlap to produce an interference pattern. So in the middle here you can see we've got this bright region which is going to be our zero order maximum or brightest point, where we have a crest meets crest or trough meets trough, and then we have alternate regions of dark fringes and bright fringes. So this darker region here in between these two bright fringes, remember, is where we have a crest meeting a trough, so that's destructive interference, which would correspond to a dark fringe. We would then have another bright fringe, dark fringe, bright fringe, dark fringe, and so on, and would have the same going on for the bottom half of the diagram. And what we want to look at here is how changing the slit separation and the wavelength will affect the fringe spacing. So right now we've got lots of fringes appearing on the screen, and that's because we're actually at the highest slit separation. However, if we decrease the slit separation, have a look at what happens to the fringe spacing. So notice how we've now got fewer fringes appearing on the screen. We've just got this central one here, but then the next bright fringe is much further away. These fringes have been spaced out, and that's because our slits have become much closer together. And remember we said that sine theta is directly proportional to 1 over d. So we've decreased little d to increase sine theta and therefore the fringe spacing, which has caused the fringes to get further apart. And we can show the opposite is true as well. So if we now increase the slit separation, notice how the fringes get all bunched up or closer together. And we can think about that relationship again. Sine theta is directly proportional to 1 over d. So because we've increased little d here, then we've decreased sine theta and therefore decreased the fringe spacing. And the second variable we looked at was wavelength. So how does changing wavelength affect the fringes appearing on the screen? Well, remember we said sine theta is directly proportional to the wavelength lambda. So whatever happens to lambda will happen to sine theta and therefore the fringe spacing. So if we increase the wavelength, notice how that increases sine theta and therefore increases the fringe spacing, so they're further apart now. Or if we were to decrease the wavelength, then that decreases sine theta and therefore decreases the fringe spacing. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.